Welcome to this mini course on the Einstein Constraint equations that we will be delivering together with Professor Jorge Lira. I am Rodrigo Avalos, and I would like to start by thanking the organizing committee of this 33rd Brazilian Colloquium of Mathematics, as well as IMPA's technical team that helped us to develop all the material that we will be presenting. And during this course, we will deliver 5 lectures, and they will consist basically on the following topics. First, we will start with an introduction to general relativity, and here we will start directly with the Einstein equations. And in the lecture notes, you will find some complementing material that starts with some rudiments concerning Lorentzian geometry, and also some background in pre-relativistic physics. But here, because of time constraints, we will start directly with the Einstein equations. And nevertheless, the idea here for us is to be able to present the Einstein constraint equations and then develop the tools related with the conformal method. And this will be the following topic. And the idea is then to present these 4 kinds of results. First, provide constant mean curvature classifications on closed manifolds. These are classical topics that go back to the work of Jim Eisenberg, and we will present these results in light of recent developments, including low regularity results and so on. Then we will go back to the asymptotical Euclidean setting and present also constant mean curvature solutions that take into account black hole initial data. And finally, in the last 2 lectures, we will discuss far from CMC constructions, first on closed manifolds and for vacuum solutions, and then for asymptotical Euclidean manifolds, also contemplating charged fluids and black hole initial data. Okay, as a disclaimer, we will not be able to contemplate gluing constructions. This was something that we announced in the video promoting the course, but due to time constraints, this will not be possible. So let us start, and we will define a space-time to be, in our case, a globally hyperbolic time-oriented Lorentzian manifold. We will work in arbitrary dimensions, so it will be a manifold with this kind of topological form. And time orientability, let us recall that it means that there is a globally defined time-like vector field that allows us to distinguish future from past. We will also impose the Einstein equations that are given by these equations here, where this is the Ricci tensor, the scalar curvature, and this lambda here is known as the cosmological constant. And the right-hand side is the energy momentum tensor field. This depends on the specific matter model, the physics involved in a specific situation. And it typically depends on the space-time metric and also on some collection of tensor fields that describe the physical situation. And let us highlight that the contracted Bianchi identity imply a local conservation law for this tensor field here, since they imply this kind of local equation. And this is going to read as a local conservation law for the matter fields involved in a specific model. Okay, so let us provide some examples of the kind of equations that we encounter with coupling the most common classical fields. And so let us start with the example of scalar field. A scalar field is basically, for us, a real valued function on spacetime, and the energy momentum tensor field associated with it has this form here given by equation 3, where we have introduced this function u, that this is a function, a real valued function that is known as the potential of the scalar field, and it depends on the specific model that we are trying to analyze. When we impose the local conservation laws for the scalar field, we can directly compute that the divergence of this energy momentum tensor field has this form. And so unless the scalar field is constant, we will have to couple to the Einstein equations with source of a scalar field. We have to couple these equations for the scalar field. For the system that we actually have to solve is this one here. Okay, and now let us analyze the case of a perfect fluid. Fluid sources are very common within physics, and they are used in settings such as cosmology and star physics, and in particular, the case of a perfect fluid is one of the simplest cases that finds applications, for instance, in cosmology. And in this case, the idea is that we have as the physical fields, the energy density, the pressure density, and the velocity field associated with the fluid. This is the energy density, this mu. P is the pressure density, and this U is the velocity field associated with the fluid. And the corresponding energy momentum tensor field is given by this expression here. And when we apply the local conservation laws for this tensor field, we find these equations of motion for the fluid. And we can simplify these equations by splitting these equations onto the parallel component and the orthogonal components to the velocity field, and recalling that when we have time-like vector fields associated with matter, we normalize them following this convention here. And what we find are that these are the equations that the energy momentum tensor field of a perfect fluid couples. So we have to couple these equations to the Einstein equations, and typically we will have to present some kind of state equation here. And a state equation is typically a link between the energy density and the pressure density, given in the form of something like this, being the pressure density a function of the energy density. Okay, here I use the letter rho for the energy density instead of mu. Well, and let us move on to the case of an electromagnetic field. This will be an important example for us in the future, and the electromagnetic field is described in space-time by a two form that we will denote by F. And in order to make contact with classical conventions, this electromagnetic field is typically decomposed according to some time-like curve that represents a physical observer into these two parts, where this represents the electric part of the electromagnetic field, and this represents the magnetic part of the electromagnetic field, where this E sub A and J, they represent orthogonal vectors to the time-like vector field gamma representing our observer. Okay, and the electromagnetic field carries its own field equations. These are given by the Maxwell equations of electromagnetism and are given by these equations 8. This is the zero differential applied to this two form. And this is the codifferential, and let us just recall that locally, the codifferential is given by the divergence taken on the first index minus the divergence taken on the first index. And here the source is the electromagnetic current density. And it also depends on the physical model that we are considering. Now, the field, the electromagnetic field F, is coupled to the Einstein equations through the energy momentum tensor of the electromagnetic field that is given by this expression 9. Okay, and since as we were saying, since the electromagnetic charge density is generated by some physical model, typically the matter that generates this charge density is going to be described by its own energy momentum tensor field. And the easiest case to present is the case of charged dust. And the case of dust is a particular case of a perfect fluid with no pressure. So if we consider this case, then the energy momentum tensor field associated with the dust fluid is going to be given by something like this, where this mu is the energy density associated with the dust fluid, and this is the velocity field. And if we assume that the particles of this dust fluid are charged, then the charge density for the electromagnetic field is given by an expression of this form 11, where here we have introduced this function Q that stands for the proper charge density. And so here we have all the ingredients to to compute the equations of motions for the matter. And in this case, the energy momentum tensor field is going to have two parts, one contribution from the fluid and one contribution from the electromagnetic field. And when we apply the local conservation laws here, we find these equations that can be computed directly. And again, we can split the above equations into a parallel component to the velocity field and an orthogonal component. And using again this normalization condition, one can then simplify the middle term to see that this is 0, and plugging in the explicit form of the current density associated to our charged dust, we see that this other term is also 0 because of this condition and the antisymmetry of the two form. And therefore, this equation becomes a local conservation of mass. And then we also find that the orthogonal component gives us the Lorentz force law. And therefore, we must couple these equations together with the Maxwell equations to the Einstein equations. So we see that in this case, actually, the full system is quite large, and it contains all these further equations besides the usual Einstein equations. And here, this is the Einstein tensor. So there are a few interesting limiting cases here. In particular, when we have no charge, then this reduces to the case of a dust fluid with no charge. And in particular, if we set to 0 the energy density, we fall into the so-called Einstein-Maxwell system that is going to be just the first 3 equations here, with this being 0. And this is also referred to as electrovacuum. Okay. And well, now that we have presented a few examples concerning the main classical sources associated with the Einstein equations, it will be instructive to present at least one explicit solution. And this is something interesting because due to the nonlinear nature of the Einstein equations, it's quite difficult to find explicit solutions. In particular, we can only find those solutions typically under highly symmetric conditions. And so these explicit solutions are usually good models for highly idealized equations, for highly idealized physical situations. And probably the most well-known situation is the one that is described by the Schwarzschild solution. And this is what we will try to review now. The Schwarzschild solution is meant to represent the appropriate geometry describing the exterior region of an isolated spherically symmetric massive body. For instance, an idealized star or even a black hole. Being the exterior region, this is taken to be vacuum, so it's equivalent to the Ricci flat condition. And the equations are posed in principle on this kind of manifolds, and here we are dealing just with the 4-dimensional case to simplify things. And well, the spherical symmetry, together with some asymptotic boundary conditions, when plugged into these equations, gives us this form for the Schwarzschild solution. This is the Schwarzschild metric. Here, R is the radial coordinate associated to some spherical coordinate system, and this is the canonical metric of the unit 2 sphere. Okay. We can clearly see that this solution is defined actually in 2 separate regions. One is R greater than 2m, and the other one is this intermediate region from 0 to 2m. And we will denote these solutions, these regions in this form. And there are a couple of remarks here. The parameter m that we have introduced is called the mass, and it actually represents the mass of the spherically symmetric body that is generating the gravitational field. And we will limit the discussion to the case that m is non-negative, which is a good physical hypothesis. And now the main issue here is trying to connect the 2 regions that are separated by the value r equal to 2m. This value, r equal to 2m, is special in the sense that it's going to represent the event horizon associated to the Schwarzschild black hole. And we will see some intuitions about this in the next slides. And in order to connect these two regions, the idea is to embed these two regions into a single vacuum solution that contains these two regions smoothly glued. Okay, and in order to do this, we will comment a little bit about the Kruskal extension. And the first step is to realize that these kind of metrics can be realized as warp product spaces for each one of these regions. Here, this P sub I with I equal to 1 or 2 stands for the restriction of the TR plane, the half plane, to either R greater than 2m or less than 2m respectively. Okay. And then these planes are furnished with this metric, where this is the function that is involved here in the Schwarzschild solution. And then we have that this metric is actually the warp product metric given for this structure. Good. And so to define the Kruskal spacetime, one first can introduce this function that is defined from the half real line of the positive numbers onto this interval. And the first thing that one checks is that this function defines a diffeomorphism. Okay, and therefore we can consider the UV plane actually something like this. We can consider and consider the region that is determined in between these two hyperbolae. And this region here is going to be denoted by Q. And in this region in between, we can define implicitly the function R via this relation here. Okay, this is due to the fact that F is a diffeomorphism. Okay, and here we can notice a couple of things. First, the level sets associated to the function R in this region Q are given by hyperbolas, this kind of hyperbolas, except for the coordinate axis that corresponds to the values R equal to 2m. Okay, and the same here. And this boundary hyperbole represents R equal to 0. Okay, and they are not parts of the region Q. Good. And so with this construction, one defines the Kruskal plane of mass m positive as the region Q endowed with this metric. And one can readily check here that this represents a two-dimensional Lorentzian manifold, and it is direct to see that these two vector fields at each point are clearly null when one applies them here. And so they define the null cones of this two-dimensional Lorentzian manifold. And therefore, we can associate the Kruskal spacetime, and that is going to be given by the warp product of this region Q with the unit sphere. So this is the metric that we associate with the Kruskal spacetime. Also, outside the coordinate axis, we define this time function, and the level sets are easily seen to be raised starting from the origin Q. And therefore, the idea is to split the region Q into the 4 usual quadrants, Q1, 2, 3, and 4, and then define the corresponding associated warp products of each of these quadrants with the unit 2 sphere. Okay. And one thing that is good to notice is that any kind of transformation that preserves the function R is going to represent an isometry of the Kruskal spacetime. So in particular, it is direct to see that this kind of transformation, this reflection, preserves this relation, and so preserves the function R. And therefore, it's an isometry of the Kruskal spacetime. So what this is saying, this is the same kind of picture that we were drawing above. That's reflections of this quadrant, the first quadrant, onto the third, and the second onto the fourth, are isometries of the Kruskal spacetime. Here we should associate to each point a two-sphere. And so we have these isometries. And then, using all these definitions, what is now interesting for us is that a straightforward computation that can be left as an exercise shows that this map from the union of the first and second quadrant onto the two half planes where the Schwarzschild solution was defined is an isometry which restricts to isometries from Qi to Pi. Okay, and so what this shows actually is that going back to this picture, this quadrant is isometric to this, and both are isometric to the exterior Schwarzschild solution. And this quadrant is isometric to this one, and they are is isometric to the interior black hole Schwarzschild solution. Okay, this is what we are saying precisely here. And thus we have found isometric embeddings of both the interior and exterior solutions into a single Ricci-flat vacuum spacetime K, the Kruskal spacetime. And so now we can connect both regions consistently. They can be pictured into a single, inside a single vacuum spacetime. And in this spacetime, we can put some structure and provide a consistent time orientation, since, for instance, this vector field is a globally defined non-vanishing time-like vector field. And so we choose the orientation that makes dt future pointing in the region K1, so in this quadrant, okay? And what we see is that the time orientation that we have chosen can be depicted in this form. So here we can realize the special significance of r equal to 2m that corresponding to the coordinate axis, since we see that these vector fields are null vector fields. Then when we reach r equal to 2m here, then every future pointing time-like curve is going to point inside the black hole interior region, and it's going to fall inevitably into this R0 singularity. And only light rays are going to be able to hover just outside this region on what is called the event horizon. And one further thing that is interesting to notice, in particular for us associated to initial data and initial data development, is that within Kruskal spacetime, we have a well-defined T0 Cauchy hypersurface that was depicted here in blue. Okay, and it contains two copies of the exterior Schwarzschild solution on each side. And therefore, going back here, the idea is to exhibit the intrinsic geometry associated to this T0 Cauchy hypersurface below. So the induced Riemannian metric on each exterior region is given by this metric here. And spherical symmetry implies that this metric must be conformally flat. Thus, we can actually write it in this form, and using spherical coordinates associated to some coordinate system xi, we can put it in this form here. And now the idea is to look for the appropriate coordinate change going from r to rho, and therefore imposing this monotonicity condition, one can compare coefficients and straightforwardly see that one has to solve this ordinary differential equation. And then imposing this asymptotic condition, one can readily solve this equation and see that the solution is given by this expression here. One can replace then this into this expression 20 here and find the conformal factor. And therefore, what one sees that the exterior Schwarzschild solution can be brought into this conformally flat form. And here we can check that this solution is actually well defined everywhere on this manifold. And actually, a direct computation shows that this region and this region are actually isometric. And each of these regions corresponds to one of the two asymptotically flat sides associated to the T0 level sets in a Kruskal spacetime. Good. So now let us go into some construction associated to the Cauchy problem in general relativity. We will merely highlight the main ideas, and the idea here is to be able to introduce the constraint equations in its internatural setting and provide some intuitions. So the idea is, if we consider a global hyperbolic n+1 dimensional spacetime, so that in vacuum our equations are Ricci flat, the objective for us is going to be to provide initial data on our Cauchy surface and then to evolve it into a solution of these equations. In this analysis, we are going to have to make a clear spacetime splitting, and therefore we introduce a parameter along the R factor that is associated with time, and we consider the global future point in time-like vector field given by dt here that is tangent to these curves. And we split this vector field into its parallel and orthogonal components to M. And the parallel one is going to be denoted by X, and it is referred to as the shift vector. And the normal components to M is denoted by the function N. It's going to be a positive function, and it's referred to as the lapse function. Okay. And using these constructions of lapse and shifts, one can build adapted local frames that have this special form here, where these coordinates are adapted coordinates to our Cauchy surface M. And the dual co-frames can be checked to have this form here. And using this kind of adapted frames, one can write the spacetime metric in this form, which is especially well suited for our purposes, okay? And here, this metric is going to be for each t constant value, is going to be the induced metric on the t constant Cauchy surface, okay? This is the geometric picture associated to the above spacetime splitting, and here actually the tangential component associated with the shift was denoted by X. And next, the idea is to look at the Ricci tensor as a PDE operator on the spacetime metric, and using coordinates, one can readily check that the Ricci tensor reads as a second order operator on the spacetime metric that has this form here. Here, what is important actually is the principal part, and then to realize that this part is given by smooth functions on their arguments, and in particular, these are quadratic functions on the first derivatives. And these functions here, f, play a special role, and they are defined by this expression here. The point here is that we have to realize that this read as a kind of system of nonlinear wave equations of the metric when we write them locally. And so we are going to have to prescribe initial conditions both on the metric and its initial time derivatives, okay? So this is what we were saying. We will need this kind of initial conditions at t equals 0. And the geometric picture here is to split the initial data geometrically on the hypersurface t equals 0 into the induced Riemannian metric on it and the initial data for the lapse and shift, which completes the initial data for G, and then provide also the first order initial data for these quantities, okay? And the first point is to realize that through standard hypersurface theory, that this quantity is going to be related to the extrinsic curvature that we are going to denote by K of this hypersurface here. And the explicit expression is well known and can be computed explicitly to have this form here. Okay, so basically the first time derivative of the induced metric is going to give us the same information as the extrinsic curvature. And our conventions on the extrinsic curvature are the following ones. So the extrinsic curvature is going to be a 0-2 tensor field on M, defined by this expression here. Here, X and Y are vector fields on M. The quantities with bar on top are extensions to the space-time V. And this is the second fundamental form that is defined to be as the orthogonal component of this derivative. And N for us denotes, again, the future pointing unit normal vector field to M. Okay, so these are our conventions for the extrinsic curvature and our conventions for the second fundamental form. And now we see that the problem is becoming somewhat more transparent. The idea is first to prescribe a Riemannian manifold and equip it with a 0-2 symmetric tensor field K that is going to play the role of the extrinsic curvature, and also the associated initial data for the lapse and shift. And then what we need to do is to find an isometric embedding of this manifold into a spacetime such that the metric on our spacetime solves the Einstein equations. In our case, that we are thinking about vacuum, it would be Ricci flatness, and such that K stands for the extrinsic curvature of this embedded submanifold. And in this setting, this is more or less the picture that we are trying to represent. And we have left outside of the above picture the initial data for these quantities. And this is on purpose, since as we will see, the initial data for the lapse and shift are going to be completely free for us to prescribe. And on the other hand, we will choose this initial data appropriately in terms of the remaining initial data in order to satisfy some requirements that will be clear in next slides. And therefore, these initial data that are related to our chosen observers along which we are going to evolve the initial data, they are referred to as gauge initial data because we have some freedom associated with them. And what is important to realize in this geometric picture is that now the Gauss-Kudati equations for hypersurfaces are going to clearly impose some constraints on G and K. So G and K cannot be chosen arbitrarily, but they are going to have to be chosen satisfying certain constraint equations. So let us recall the Gauss-Kudati equations for hypersurfaces. Here again, everything that has a bar on top is referred to space-time quantities, and things that don't have a bar on top are constructed with the induced Riemannian metric G on M. Okay, so this is the curvature tensor on space-time and the curvature tensor on M as given by G. Okay, so we see here clearly that the induced metric G and the extrinsic curvature have to satisfy these constraints in order for us to be able to even think about posing the initial value problem appropriately. And in fact, the constraints that they pose are explicitly given by this proposition. So the idea is that if we have a space like hypersurface, isometrically immersed in a Lorentzian manifold satisfying the Einstein equations, here we assume that we may have some source and also some cosmological constant. Then G and K are subject to these constraints that we will still refer as the Gauss-Kudati constraints equations. Here, this defines the induced energy density, and this defines the induced momentum density by the energy momentum tensor field. And let us at least sketch the proof of this proposition. It is quite straightforward and follows techniques that are quite well known in Riemannian geometry. So the point is, if we pick first an orthonormal frame where always n is our future pointing unit normal field, then from the Gauss equation, we can take these two traces out of the space-time curvature tensor. And here we have used the Gauss equation to take the traces on the right-hand side in terms of the intrinsic geometry of M and the extrinsic curvature to M. And we can see directly that this is going to be the norm squared of the extrinsic curvature, and this is going to be the trace squared of the extrinsic curvature. These are these two quantities, and this double trace here is clearly going to produce a scalar curvature. And now the idea is that if we write the Ricci tensor associated to the space-time metric using these frames, and we compute it along these space-like vector fields, then opening this computation, we find this expression here. Okay, so here, if we were to take a second sum over I equal to j, so tracing this equation, we see that the resulting expression here is precisely going to match this one. And that's here we're going to find something like Ricci on the normal direction. Okay, so we can replace this expression here by this traced plus the Ricci on the normal direction. Doing that, this is what we have done here. We find this first line, and then we can add and subtract the Ricci on the normal direction and do a few simple manipulations. Here we find the scalar curvature of the space-time metric, and therefore this builds the Einstein tensor of the space-time metric, and using the Einstein equations, it is rewritten in terms of the energy densities of our model. So defining this by the energy density, we found here the Gauss constraint. And we can do something similar with the Codazzi equation. So we start computing the Ricci on these directions, the normal direction and a space-like direction. We open these computations and we see that the zero component here due to the anti-symmetry of the curvature tensor is going to kill the first term. And we find that this is all that survives. And then here we apply the symmetries of the curvature tensor to commute these two vector fields with these other two. And once we do that, here we can apply the Codazzi equation directly. And once that is done, the Codazzi equation transforms into the momentum constraints straightforwardly. All that we have to realize is that this component is given precisely by these components of the energy momentum tensor field, and then applying our definition for the momentum density, we find our momentum constraint. Okay. So now we see that the Einstein constraint equation presented above, that's are a consequence of the Gauss-Codazzi equation for hypersurfaces, are necessary conditions for the initial value problem to be well posed. It is a remarkable fact, which goes back to the pioneering work of Yvon Choquebrois, that in most situations that are of interest for us, these are also sufficient conditions. And to see this, let us sketch how this is done in the case of vacuum. One first equips we embed our Cauchy surface into a product manifold of this form, and then we fix a background metric of this form on spacetime, where E is going to be some complete smooth metric on M. And then we can rewrite the Ricci tensor as we did above, but rewrite the Ricci tensor of our spacetime metric G bar, but in terms of the covariant derivatives associated to the metric E hat. Everything that has a hat on top is a quantity that is constructed with this E hat metric. So we have basically an equation that has the same form, but now these f functions are actually vector fields that are defined by this expression here. And again, these small f with a hat on top are the components of a tensor field that depends on the space and metric and its first covariant derivative. And they are in particular quadratic functions on the derivatives of the space and metric. And the idea here is to neglect the terms that involve this function f and consider here a reduced tensor that we call the reduced ridge tensor. The idea is that these equations that are both in terms of the reduced ridge tensor, they read as a quasi-linear system of wave equations where we can apply some standard PDE theorems to guarantee that these equations have a unique solution. And here we have to pose things on appropriate functional spaces and so on, but we're going to skip that part for now. And so the solution to this problem provides us with a Lorentzian metric, at least for short times. And the objective is to show that actually this solution to these equations solves the original equations. And for that, we in particular are going to show that this condition holds for our solution. In order to do that, let us first notice that if we plug this solution that we obtained into the Einstein tensor, we see that the Einstein tensor associated with this metric has this form. Then one can use the contracted Bianchi identities and manipulate them a little bit to see that the Bianchi identities imply that the vector field F satisfies a system of homogeneous linear wave equations. And these equations also have unique solutions when we set things in appropriate spaces. And so in particular, we see that if the initial conditions for the vector field F satisfy this condition here, then the solution has to vanish identically. And these two conditions can be further simplified by a straightforward computational exercise, which shows that if the initial data for our space-time solution solves the vacuum constraint equations, which was a necessary condition anyway, and if furthermore we pick our initial data so as to satisfy this condition, then this other condition comes for freely. And then the idea is to be able to satisfy this second condition. And in order to do that, one first fixes the initial data for the lapse and shifts arbitrarily, for instance, by picking the initial data for the lapse equal to 1 and for the shift equal to 0. And a straightforward computation using adapted frames shows that this condition reads as these two equations equal to 0. And then one can see that we can fix the first order initial data on the lapse and shift so as to satisfy these two equations, which are equal to the condition 2. And so finally, what we see from the above discussion is that the corresponding solution to our reduced equations, if we construct it with initial data such that we solve the vacuum constraint equations, the lapse and shift satisfy these conditions, and the first order initial data are picked so as to satisfy this condition here from this relation, then actually our solution of the reduced equation solves the full vacuum Einstein equations. And we have a short time solution, a Cauchy element of our initial data. Okay, there are a few remarks that are interesting to make at this point. The first one is that this choice here, although arbitrary, it doesn't pose any fundamental problems due to something that is called geometric uniqueness. That basically says that if we have two initial data sets that only differ by our choices on the initial data for the lapse and the shift, then these initial data sets evolve into isometric spacetimes. So we have geometric uniqueness. And related to this, there's also a celebrated result by Shuker and Robert Garrock that states that there is a unique up to isometries maximal globally hyperbolic development of any vacuum initial data set. And also we have good causality properties that exhibit finite propagation speed associated to the solutions of wave equations. And in fact, in particular, the maximum speed is given by that of the null curves of the solution. And also one can incorporate matter content quite straightforward into the about picture. And in particular, one can incorporate the kind of examples that we provided at the beginning, scalar fields, electromagnetic fields, and also some fluid sources. And for precise reviews of all these with precise statements on functional spaces and regularity properties, we would like to refer the interested reader to this textbook by Yvon Chouquet-Brois and also this other textbook by Hans Ringstrom. And one thing that we should highlight is that when we couple matter fields, in particular Yang-Mills fields, and it includes the electromagnetic field, these fields can impose further constraints on the initial data. For instance, if we were to couple a charged fluid, we saw that we have to give initial data for the electromagnetic two-form and also for the fluid. Here we are thinking about a perfect fluid. And the initial data for the perfect fluid is completely free. It doesn't impose any further constraints, but the initial data for the electromagnetic field impose constraints. And if we recall the Maxwell equation for the electromagnetic field, one can directly see that if we project this equation on the normal direction, then we get a constraint that is given by the Gauss law. And if we restrict this other equation to tangent vectors to M, then this is going to imply that the induced two-form on M have to be closed. So these two equations impose these two constraints on the electric and magnetic parts of the electromagnetic field at t equal to 0. Recalling here our convention on the electric field, and this is the definition of the induced charge density by our charge current. And so the full constraint system is going to read like this, which is a much larger and sometimes it is more complicated to deal with. Now, let us give just a quick example. If we use the Kruskal extension for the Schwarzschild spacetime, we have already provided the initial data for the induced metric. And clearly due to the fact that this is static in our coordinates, we can directly see that the T0 Cauchy surface is totally geodesic. And this reduces the above constraints into this scalar curvature constraint that can be explicitly checked for this kind of metric. Finally, we would like to close this first lecture by talking about black hole initial data. And our objective is to provide suitable conditions on initial data sets that can characterize initial data sets that should evolve into black hole spacetimes. And let us just recall a few facts about this kind of spacetimes. First is that typically black hole regions are defined appealing to certain conformal completions. But we will not do this. This is very useful and many very nice theorems can be proved appealing to conformal completions. But for us, the major drawback is that in order to know what the black hole region is appealing to conformal completions, one needs to know the whole spacetime beforehand. And since we are trying to actually generate spacetimes by evolving initial data sets, this is not what we want to do. And so we want a treatment that is amenable to initial data analysis. Okay. And for this, we will just do here a brief detour into singularity theorems, and in particular, this singularity theorem that is celebrated and that is due to Roger Penrose. It basically says the following: that if you have a spacetime that satisfies this curvature condition here, where V are null tangent vectors, it has a non-compact Cauchy surface, and it possesses a closed trap surface, then the spacetime cannot be null geodesically complete. In the above theorem, what is important for us is this new concept of trap surfaces. And basically these are in an n+1 dimensional spacetime, these are going to be n-1 dimensional closed space-like submanifolds, along which all future pointing null orthogonal geodesics are converging. And this is going to be a condition that is going to be translated into conditions in our initial data sets. Okay, so basically the picture is something like this. We have some space-like hypersurface within a Cauchy surface, and we have light rays that would typically escape to infinity and go inside our black hole region. Here, this is the unit pointing, outward pointing unit normal and the future pointing unit normal. And the point is that this would be depicting a normal situation. And in the case of a black hole region, what one expects is that all the future pointing light rays are actually converging. So there is here a region from which light cannot escape to infinity. And the above theorems, similarity theorems, have many useful extensions. In particular, they have been established under other hypotheses. And here there is a small review of other results. And for us, although these similarity theorems are not telling us what is actually going on near the singularity, in order to avoid certain pathological behaviors, Penrose also proposed this idea of cosmic censorship that basically states that generic singularities are hidden within black holes. So the presence of these singularities that are guaranteed by these singularity theorems would be a signature of black hole spacetimes under this cosmic censorship hypothesis. We should caution everyone that giving actually a precise formulation of cosmic censorship is not easy, but there is a particularly nice one by Demetrios Christodoulou, who has actually established what is, to the best of our knowledge, the only proof of cosmic censorship under spherical symmetry in this paper here. And we're going to accept the validity of this conjecture, at least as a working hypothesis, so that when we are dealing with non-compact Cauchy surfaces, for instance, we have a way of characterizing black hole spacetimes in terms of the conditions of the singularity theorems. And for a discussion on the status of the cosmic censorship, we refer everyone to this paper by Robert Wald. And the idea is to characterize trap surfaces in terms of initial data sets, and therefore let us consider a Cauchy hypersurface with boundary. It may have many connected components, and we will fix a particular one. And since we are assuming that our spacetime is time orientable, we have a future pointing unit normal, it's denoted by n, and also since sigma is a boundary component, we have an outward pointing unit normal field denoted by nu here. This is depicting this figure. And then we can define the null vector fields at any point of our hypersurface, given by these expressions also, as was depicted in the previous figure. And they provide a basis for the orthogonal space to sigma. Okay. And we can consider the null geodesics that have as initial conditions these null vector fields, and they rule null hypersurfaces within spacetime. And we can use extrinsic geometry associated to these null hypersurfaces. In particular, we can define the null extrinsic curvatures using our usual conventions are given by these expressions, one extrinsic curvature for each normal null vector field. And their trace induces the null mean curvatures that are also known as expansion scalars. And these have the usual interpretations in terms of divergence of the null vector fields. So they provide us, putting a sign on these expansion scalars actually provides us with a characterization of the convergence conditions for the null vector fields across our hypersurface, our surface. So this kind of condition is the one that we are looking for to characterize a trapped surface. Okay, and as we will see below, this kind of condition can be recast in terms of our initial data set. This is the proposition. So as we were saying, the interpretation is the usual one for the null mean extrinsic curvatures. And A direct computation that we will not do here due to time constraints actually shows that the null mean curvatures can be written in terms of our initial data set. This is the extrinsic curvature. And this K here is the extrinsic curvature of sigma as a hypersurface of M, while H is the induced Riemannian metric on sigma by the Riemannian metric G of M. Okay, so this here is representing the mean curvature of sigma as an embedded hypersurface in M. Okay, we will not go into the proof, but the important thing is that we can write expansion scalars in terms of initial data sets, and we have the right interpretations for them. And this proof can be consulted in the lecture notes in detail. For us, the important thing is that now we can define a trap surface by this condition of convergence on the future pointing null curves across sigma. And we would say that a marginally trapped surface is given by this condition with the not strict inequality. And we also define an outer marginally trapped surface only by the condition that the light rays pointing outwards are converging. And an apparent horizon is given by this condition here. So for weakly second-order spacetimes, due to singularity theorems, these conditions are going to translate into the existence of black hole regions in the evolving spacetime. And as we said, this can be characterized in terms of initial data sets. And just to provide an example, again, going back to Schwarzschild, we know that the initial data for Schwarzschild is totally geodesic. And so in this case, the expansion scalars are going to be given in terms of the intrinsic traces in terms of the mean curvature of sigma as embedded hypersurface in M. And one can do an explicit computation here to see that what we know to be the event horizon of Schwarzschild, that is given by this region here, is actually totally geodesic. And therefore, we have here an apparent horizon in the case of Schwarzschild. Okay. Just a few comments before ending this first lecture. First, trap surfaces actually tend to appear inside black hole regions, not as event horizons, as we saw in the case of Schwarzschild. And although one can expect that putting trap surfaces sufficiently far apart is going to make each trap surface evolve into an independent black hole, this is not so easy to see. And this can be consulted, for instance, in this paper by Cruciel and Reis-Maceo. And nevertheless, this is a canonical way to address this problem in a systematic way, which is amenable to initial data analysis. And for instance, this is highlighted in this paper by Sergio Dain. And one of the nicest constructions that we will do along these lectures is given by David Maxwell in this paper here. So we will start with our analysis of the constraint equations in the next lecture.